We're going to look now at the variance and the standard deviation. So suppose we've already got the mean of a sample, right? We take a sample, we get the mean. Now what we want to do is we want to get a measure of how spread out the data is from that mean. Is it compacted around the mean, or is there a pretty good spread, pretty good distance away from the mean? Here's how we're going to do this. We're going to develop a formula for this. So suppose that x sub I is a piece of data. Now don't let that I get you upset. All that I is just a subscript which indicates a name for a piece of data. Like it could be, you know, if I write x sub I, it could be that I could be 1, 2, 3, whatever. So we could have what? X sub 1, x sub 2, x sub 3, x sub 4, and I could be any number, so maybe it's this one. Okay, all it says is that if x sub whatever is a piece of data, all right, so I could be, you know, the first piece, the second piece, the third piece, and so on. So if x sub I is a piece of data, now before we go on, let's be sure we understand what this is. X sub I, remember those subscripts are just names. You know, I could be, let's write it down here. Maybe I could be 1 or 2 or 3 or, you know, whatever number. So you might have x sub I might be x sub 1 or x sub 2, x sub 3. So that I is just a name for this piece of data. It could be the first piece, could be the second piece, the third piece. So when you say x sub I like this, you're just saying you've got some piece of data. It could be the first, second, third, or whatever. Okay, so suppose that x sub I is a piece of data. So you got some piece of data. And in that data set, x bar is the mean. All right, so x bar will be the mean. So you got a set of data, x bar is the mean, and then you pick a piece of data. So you got the mean and some data value. All right, so what we want to know is how far is this data value here from the mean, right? This is a measure of dispersion, so we're looking to see how the data is spread out from the mean. So what we're saying is this. How far is x sub I from x bar? X sub I is this. X sub I minus x bar units away from x bar. Okay, let's make some sense out of that with a numerical example. So suppose we've got a data set and we compute the mean, right? So the first thing we do is we compute the mean and we get 20. Now, pick a piece of data from this collection. Maybe we pick 26. So what we want to know then is this. How far is 26 from 20? Okay, well, you know how to do that, right? It's going to be what? 26 minus 20 is 6 units. All right, so how far away from the mean of 20 is this data value, 26? It's going to be 26 minus 20. All right, now look what we've done here. This is going to be our piece of data minus the mean. All right, so how far is a piece of data from the mean? You just take that data value, subtract the mean, and that'll give you the number of units. Let's draw a picture here. So suppose that we have, I'll do it up here. All right, so here's the, say our x values, and maybe here's the mean. All right, here's the mean right here, right? It's a middle value. Now, pick some number, maybe I'll pick this one over here. Okay, I'll call that x sub 1. Okay, so how far is x sub 1 from x bar? Well, it's this far, right? And how do you measure that distance? It's going to be x1 minus x bar. So in our example here, if that's 26 and this is 20, what would we get here? We'd get 26 minus 20, we'd get 6 units. But now it could be, too, that x value that we pick is over on this side. Okay? I'll call that another value, x2. All right, so how far is x2 from, how far is x2? You know what, let me make that a dot, how far is x2 from x bar? It's going to be that same measure. What we're going to do is just take this. We're going to take x2 minus x bar. Like suppose this was 15 and that's 20. Where would we be? Up here at the top. How far? 15 minus 20 is negative 5. So we get this. 15 is negative 5 units from 20. Just meaning the negative. The negative means, let's say below. I'll write it that way. Below. Okay, so it's below the mean. So if you get a negative number, you know that data value is below the mean. All right, so how do we measure how far a piece of data is from the mean? We compute this right here. Data value minus x bar. Now this number right here, x sub I minus x bar, that is called the deviation score. Because it's a score that tells us how much of a deviation we have between our data value and the mean. Okay. Let's take a look at an example. I'm going to use these numbers here. And we actually use these, if you remember back in one of our examples when we found the mean. Right, here's a data value, and then I'm going to measure x sub I minus x bar. All right, so suppose that the data values are 6, 8, 13, 10, 8, and 9. Okay, so suppose we've got these, what do we have here? 1, 2, 3, 4, 5, 6 data values. Now, we did this in the last example, but if you wanted to find the mean, what would you do here? To find the mean, what would you do? You're going to add all these up and then divide by 6. Okay, so if you do that, it turns out that x bar equals 9. Okay, you can try that. Just add them all up, divide by 6, comes out to 9. Now, how far is each one of these scores from 9? Okay, well, look, let's just do this. It's 6 minus 9, negative 3. So that says that the 6 is 3 units below the mean, right, because of the negative. Then you get 8 minus 9, negative 1. So 8 is 1 unit below the mean. 13 minus 9, and that's 4. So 13 is 4 units above the mean. 10 minus 9, that's a 1. So the 10 is 1 unit above the mean. 8 minus 9, okay, again we're at negative 1. And 9 minus 9, that's a 0. So 9 is no units away from the mean of 9. Now, it seems reasonable that, I'm right down here. It seems reasonable that if you want to get the total amount of deviation, right, that's what we're trying to do here, right? Back here at the top, we want to get the measure of the spread of the data from the mean. So I've got each individual spread. Now, to get the total, why don't we just total these things up? So just add all the individual data deviations together. So here's what it's going to look like. Okay, remember that symbol? The summation, I'm going to add these things. X sub I minus x bar. Okay, what does it say? All right, don't let the notation get in your way. This just says to do what? Add up these things. Okay, and what are these things? Those are just those deviation scores. Okay, so I find that each individual deviation, and it just says add them all up. Okay, so if it turns out then that if you add all these up, let's do it down here. What do you get? Okay, where are we? Negative 3, negative 1, negative 4. Plus 4 is 0. 0 plus 1 is 1. 1 plus negative 1 is 0. Plus 0 is 0. Okay, this total deviation is 0. Now, this happens every time. All right, this is always 0. For any set of data, that sum of the deviation scores is always going to be 0. And it's just always 0 because you get things that balance each other off, right? That x bar is a middle value. So what happens is that, like here, the -3 and the -1 balance off the 4. The 1 and the -1 balance off the 1. So we're always at 0 here. So if we can get it down here, let's say this. So this thing right here is no use to us. All right, that is of no, you know what, I don't want to say it's of no value. It is, yeah, let's say this, is of no value as a measure. Okay, so that one doesn't help us. So we need to come up with something else. And here's what we do know, right? If you square a number, so I'll write this. Squaring a number always results in a positive number, right? So if you take any number at all, well, except 0, squaring a number always results in a positive number. All right, so in that last problem, when we added up those deviation scores, we had some negatives, some positives, and they always offset each other's. All right, so what we're going to do is we're going to get rid of those negatives by squaring numbers. So we will use, all right, so instead of just using that x bar, that xi minus x bar, okay, I'm going to leave a little space here. Here's what we did before, and we got zeros, right? If you add all those up, you get 0. So let's change it. So we're going to square those. So now what we're doing, and we'll do a numerical example in a minute. So what we're doing now is we're adding up what? These numbers, but we're squaring these numbers first, right? So square all those differences and then add them all up. Now this right here, this is called the sum of squares. All right, so we could just abbreviate it. SS is this, x sub I minus x bar squared. And that is called the sum of squares. Now, I'm using x bar, so this is for a sample. So that's the sum of squares for a sample, and it's a sample because I'm using x bar, right? And x bar, English letter, comes from a sample. But then I can also write this, okay? If I write SS equals, if we wrote this one, x sub I minus mu, right now that Greek letter, you know, that means it comes from the entire population. So this would be the sum of squares for a population. All right, so the point of all this is, do you see that what we're doing here is we're adding up these differences? And what are the differences? I'll go back a page here. The differences are what? All right, down here, I'm at the bottom right, down here. What are those differences? Those are the spreads. I'm just measuring the spread between a piece of data and the mean. All right, so I've got all the individual spreads. All right, that's xi minus x bar. But that always, if you add those, that comes to 0. So let's get rid of the negatives, right? Get rid of the negatives. We'll turn them all positive if we square them. All right, so that's what we did over here. We just squared them. So I'm going to do that in an example right now. So here's our example. Let's use the same one, x sub I, and then we'll take x sub I minus x bar, and then we'll write a column for squaring it. Up, x bar. We'll square that. Okay, so the x's that we had were 6, 8, 13, 10, 8, and 9. Now, we computed the mean. We didn't actually do it, but you could do it, right? If you add them all up, divide by 6, right? 6. 1, 2, 3, 4, 5, 6. All right, you get x bar to be 9. All right, so here's what we did. 6 minus 9, I'll do it. 6 minus 9, negative 3. Now, What's the next column? Bring it over here. Square it, all right? So you just get this, right? So I won't write it for all of them, but you get negative 3 squared. The next one, 8 minus 9 is negative 1, so you get negative 1 squared. Okay, let's do them. Negative 3 squared is 9. 1 squared is 1. All right, 13 minus 9, 4. 4 squared is 16. 10 minus 9 is 1. 1 squared is 1. 8 minus 9 is negative 1. Negative 1 squared is, right, negative 1 times negative 1 is 1. And 9 minus 9 is 0. 0 squared is 0. All right, now, we know if we add these things up, right down here, if you add these up, you just get 0. Every time, any data set. But if you turn those negatives to a positive, then when you add these up, you get a positive number. So what do we get here? Let's do it. What do you get? 9 and 1 is 10. 26, 27, 28. All right, so we get 28. So in our case, I'll do it up at the top right. The sum of squares is 28. You know what, let's do an example here. There's a slight problem with that 28, right? Because we squared all those numbers. And that's supposed to be giving us a measure of how spread out the data is. Let's get a feel for what we're going to do here. All right, so suppose that for 6 days, you observe ducks flying over your house. Okay, so every day for 6 days you observe ducks flying over your house. So each day you count the number. You count the number of ducks. I can't write here. All right, so suppose this is what you get. On day 1, you get 6 ducks. On day 2, you get 8 ducks flying over your house. Day 3, 13 ducks. Day 4, 10 ducks. Day 5, 8 ducks. And day 6, 9 ducks, okay? So these are all ducks. Now, if we start looking at this, at these distances, this is going to be what? All right, so the average is what? 9 ducks, right? So if you just had to make a guess, what's your best guess for the number of ducks that flew over your house? The best guess would be 9. Okay, but now we know it's going to differ a little bit. So let's get the deviation scores. All right, so what we would have is, I'm going to carry the units here so you can see what happens. 6 ducks minus 9 ducks, that's negative 3 ducks. But then you square it, okay? So I'm going to square it. So what do I get? I get 9 square ducks. Okay, I'll write it. 9 square ducks. Now, that is just an odd thing to say. I got 9 square ducks. Now, if this happened to be inches, I'll write it here. What if we were dealing with inches? If I write 9 square inches, you'd be okay with that, right? That's just some kind of an area. But we're just not used to this thing with 9 square ducks. So the square comes from the fact that we wanted to get rid of those negative signs, so we squared everything. But it gave us a problem. We get these oddball units. So how do you think we're going to get rid of the square? We're going to take square roots. Okay, so we'll do that eventually. We will eliminate the square by taking square roots, okay? So, but before we get there, let's talk about the variance while we're still with the squares. So the variance. This is going to be one of the major measures that we use for variation. So the variance is the mean, just the average, right? It's the average of the sum of squares. Now, just some notation. If you write an English letter, and I'm going to put the square on it just to remind us that things are squared, right? We squared everything, sum of squares. If you write S squared, this is the sample variance. And if you write, all right, now here's another Greek letter. If you write sigma squared, this is the population variance. Now, this is a lowercase sigma. Right, the uppercase was this one. Remember this one? Summation. That's an uppercase. All right, so if you use the Greek letter, you're talking about the entire population. If you use an English letter, then you are talking about a sample. So here's the variance. The variance is going to be, all right, so S squared is going to be this. Now I'm going to write it a couple ways. It's the sum of squares over n minus 1, and sigma squared is the sum of squares over just capital N. Now, what I'm going to do here is I want to write this all the way out. Because this looks like, okay, to get this, I have to get this, and to get this, I got to go someplace and look it up. So here's the exact formula, okay? It's going to be this. S squared is equal to, all right, n minus 1 in the bottom, sample size minus 1. And the sum of squares, remember, was the summation of x minus x bar. I'm going to get rid of the i's, right? As long as I have x, just take all the x's, all the individual x's, subtract the mean, get that number, add them all up, and then square it and divide by the sample size minus 1. And then here's what you get for sigma squared. Sigma squared is, all right, almost the same thing. It's the sum of those x minus x bars, those deviations, squared just over the population size. So here are two, these are called defining formulas. These are how these terms are actually defined. The variance is defined this way for a sample, this way for a population. Now let's just talk about this denominator here, n minus 1. You know, small n, lowercase n, that's the sample size. So why do we divide by n minus 1, right? 1 less the entire sample. Well, here's why. We divide by n minus 1 rather than n because we actually have only n minus 1 observations. All right, now think about this. What if you had 10 pieces of data and you're going to add them together, right? And you get, say, 50. There's 10 numbers, you add them together and you get 50. Now, if you're given 9 of those numbers, right, 1 less than the 10, if you're given 9 of those numbers, are you free to choose anything you want for the last one, or is it already determined? Right? If you add up 10 numbers and you get 50, and you're given 9 of them, that last one's already determined. So it's not really a new observation, right? It's not variable anymore. It's determined. So I'm going to write some formulas here. These are the defining formulas. So a couple we've already had here. So S squared is equal to, all right, that's the sum of this x minus x bar squared over n minus 1. Now this one here, that is the defining formula for the sample variance. And in this case, the data is given individually. All right, the data is not given in a frequency table. You've got all the individual pieces of data. Then the next one is going to be for the population, so we're going to write sigma squared. That's equal to, top is still the same as the last one, the summation of x minus x bar squared over n. That's the exact population size. Not n minus 1, but just n in this case, all right? So this is the defining formula for the population variance. And again, the data is given individually. Now, these formulas are a little bit difficult to work with by a pencil, because what do you have to do each time? Look at all the works involved here. You have to get, all right, and this one up here, a lot of work here. What do you have to do? You need all your individual pieces of data. Then you have to get the mean, right? So you have to add them all together, divide. All right, so there's a bunch of operations here just to get the mean. Then you have to make all these subtractions. Then you have to square all those results. Then you have to add all those up, all right? And then you have to make a division, all right? That's just a lot of individual computations. So what we're going to do, now we're not going to do this, but you can, with some algebra, you can convert this formula here, you can convert this formula here to a new one, all right, by knowing some algebra. I'm not going to actually do this. I'm just going to give it to you. Here is what you would do. You're going to write this. S squared is equal to, all right, kind of a long fraction. Here's the top. N times the summation of x squared, right? So what you do here so far is you take the sample size, multiply that by this. Now what is this? This is the sum of all the individual pieces of data squared. So you look at all your individual pieces, you square them. Square each individual piece. We'll do an example. Then you add them all together. Then you multiply by the number of pieces of data you have. Then you subtract. Now be careful here, it looks almost the same. You subtract the sum of the x's squared. Now be careful here. You see the difference between these? What does this one say to do here? This says to take each piece of data, square it. Right? So you take all your individual pieces, you square it. Then you add them up. What do you do over here? Oh, this says to add up all the individual pieces and then square that result. Slight difference. Okay, and then you divide by, now, this slight difference in the denominator, because what we're doing is we're converting this algebraically to a new formula, which is n times n minus 1. Now, this formula is built into calculators. But you may be asked to do this sometime, you know, if it says use the defining formula, if your directions are to use the defining formula to find the variance, this is what you would use. All right, so this is called the computing formula. Okay, these up here, these are the defining formulas. You could also just use the computing formula, which is a little faster. Computing formula for variance. Well, I think we should probably do an example. So here's a set of data. All right, I'm going to use those same numbers, right? We had 6, 8, 13, 10, 8, and 9. Too close. Okay, so the first one, what I'm going to do is this. Use the defining formula to compute s squared. All right, so this is the defining formula. So I'll write that formula. It's this. S squared is equal to, add up these things and divide by n minus 1. Here's what I found really useful. If you're going to do something with a formula, write the formula. Write the formula so you have it right in front of you. The directions are right here. So what does this say to do? It says to do this. You're going to make some additions of what? Take a piece of data, subtract the mean, and then square them. All right, so here's what that's going to look like. S squared would be, okay, now, do you remember this? X bar was equal to 9, right? If you add all these up, divide by 6, you're going to get 9. Okay, so here's what you have first. X minus X bar. Now, the first X I see up here is 6. So I'm going to have this. Now, it's a fraction, so I'll write on the top. It's going to be the quantity, 6 minus 9 squared, plus, now go to the next piece of data, 8. So it's going to be quantity, 8 minus 9 squared, plus, go to the next piece of data, up here at the top, 13. 13 minus 9 squared, plus, next piece of data, 10 minus 9 squared, plus 8 minus 9 squared, plus 9 minus 9 squared, all over sample size, write n, right here, n, which is 6, minus 1. Okay, now, this is going to be negative 3 squared plus negative 1 squared plus 4 squared plus 1 squared plus negative 1 squared plus 0 squared. Now, we actually did this in the last example using that table. I'm just not writing the table this time. All that over 5. All right, so now we get what? 9 plus 1 plus 16 plus 1 plus 1 plus 0 all over 5, right? And that gives us that 28. You remember that 28 over 5. And this gives us, all right, now 5.6. Now, I don't need to round because it comes out to 5.6. Now, remember, the original data is given to the ones place, right? The accuracy is to the ones place. You know, I don't have any decimals out here. So I'm going to, since this is to the ones place, I'm going to round off to 1 digit more. Round off to 1 digit more. So instead of 5 or 6, I'm going to round off to that 5.6. But remember, this is all squared, so this is square units. It's like square ducks. Okay, so I got 5.6 square units, 5.6 square ducks. All right, so that is one way to get that sample variance. Okay, this is the sample variance using the defining formula. Now, let's find the variance using the computing formula. Here's how it goes. S squared is equal to, all right, so it went like this, was this fraction, n times the summation of x squared. So this says add up the squares of the individual piece of data. Take each individual piece of data, square it, add them up, minus, and then you do this all at once here. Add up all the data values, add them all up first, and then square it. Divide by n times n minus 1. Let's make a table. We'll make a table for this. So in the table, look at what you need. You need x. You need x squared. You need, okay, then some of the x's. Not too much that we need here. So I'm going to make a column for the x's, and then a column for the x squareds. Okay, I think that should be it. So here's the x's, right? What were the x's here? Make sure I get them right here. It's 6, 8, 13, 10, 8, 9. Now, if I square these, I'm going to get 36, 64, 169, 100, 64, 81. But now what do I want with these? Okay, so I've got all the x's. I got their squares. Now what do I want to do? Oh, I want to add up the x squareds. So add these up. But then I also want to add up just the x's. Okay, so add up the x squareds, add up the x's. Now, if I add up the x's, when I added up the x's, I got 54. When I add up the x squareds, I got 514. Let's put everything into our formula. So s squared is going to be n, which is 6, times the sum of the x squareds, right? The sum of the x squareds, which is 514, minus the sum of the x's, right? Here we are. The sum of the x's, which was 54, but then I square it. Minus 54 squared, all over n times n minus 1. 6 times 6 minus 1. All right, now here's what I got when I did these. 6 times 514, I got 3084. Minus 54 squared, 2916. Oh, what happened there? 2916 over 6 times 5. All right, now, 3084 minus 2916 is 168 divided by 30, which turns out to be 5.6. Okay, square units again. So I got the same number. It's just that the computations, I think, are a little faster. It might not show it in these two examples because I've got only 6 numbers, but if you add 600 numbers, this formula here, this computing formula is much faster. And this is the one I think that's built into software packages. Now, there's one more important idea in this unit right here, and that is, let's just do it right here, the standard deviation. So you remember, back here, if these were ducks, right, if you know, remember we had that example where if these are the number of ducks that fly over your house every day, you get an average of 9 ducks a day. And then when you compute this, you get, 5.6 square ducks. All right, so get rid of the square. So if you know that if you take the square root of something, it's going to be positive. So here's what I'm going to write. If I do this, I'm going to call this s, because this is the square root of s squared, right? Do you believe that? If you want to write it this way, what's the square root of s squared? Well, typically, now I know s is a positive number. S is a positive number, so this is just going to be s. And this is called, well, here's what I do. I take the square root of the sample variance, and this is called the standard deviation. All right, so S, here's the formula for S. I'm just going to write the defining formula. It's a big square root. Okay, it's the square root of, square root of what? Square root of all of this. So let's write it in there. N times the summation of x squared minus the quantity summation of x's squared over n times n minus 1. All right, this is the computing formula. That's the computing formula for the sample standard deviation. So let's wind this up here. What do we get for ours? We know that s squared is 5.6 square units. And then s, well, that's going to be the square root of that 5.6 square units. So s is equal to, now, square root of 5.6, I'm going to write this all the way out. Here's what I got. I got like 2.366 ... Okay, now when you take the square root, take the square root of the square, you just come back to regular old units. All right, so when we square the ducks, you get squared ducks. When you take the square root, you just take the square root of the square of ducks, you just get ducks. All right, now rounding. Our original data is accurate to the ones place. So I'm going to round this number here off to 1 decimal place. Now, I'm going to round it off to this position. I look over here, it's above 5, so I'm going to round this up. So I'm going to say that the standard deviation here, how about an abbreviation? Standard deviation is 2.4 units. Remember what that standard deviation does? It gives us a feel for how many units each piece of data is from the mean. So I'm going to write this down, and then we're going to be done with this section. So the standard deviation, that's an average amount of deviation from the mean. So you have a bunch of data values. On the average, how do they differ from the mean? Like, for example, suppose you have this. Okay, suppose that you have the mean, x bar. Now, what if you have a large standard deviation, a large S? Okay, that could mean like your data is, pretty spread out. It's not compact. There's a lot of spread. But suppose that you have a small standard deviation. All right, that means, if it's very small, that means the data is pretty compact around the mean. All right, that takes care of it for this discussion here. In the next little section, we'll talk about what do you do if the data is given in a frequency table.